Time is 12:30, so let's begin here. So today we will finish up the summarizing and managing data section. We will do matrix algebra. Next time we'll just finish up some remaining things. We will also review for the exam, so please bring questions if you have them regarding the exam. Our final exam will be Friday, December 16th at 7:30 a.m. Are there any questions? Okay, so we left off last time on page 5 of the notes. We're talking about various ways that one can reconfigure your data or get the data in the correct form so that you can analyze it. And a new function for us that can be quite useful is what's called the Reshape function. And basically this plays the same role as proc transpose in SAS. And so what it allows you to do is basically take, let's say, a wide format to a data set and make it a long format, and vice versa. You'll see what wide and long formats are shortly. These are the more commonly used terms. Very often, I think we did this in terms of proc transpose, when you have some kind of longitudinal data set, where let's say maybe every column represents the response at, let's say, time 1, time 2, time 3, and so on. And that's often referred to as the wide format. And then oftentimes you want to reconfigure it so that now all those responses are actually in one column. Very frequently, procs in SAS or functions in R require a format like that to actually analyze the data. Okay, so this is a very simple setting. Let's say that I have some data frame that we're going to call set 1. And inside this data frame, I simply have, let's say, maybe 3 people. We'll call them subject 1, 2, and 3. Each of them has an identification number, a unique identification number with them. Each of them has maybe, you could say, like a covariate or explanatory variable or an independent variable with it. And I simply call this particular covariate age. And then we have responses at time 1 and responses at time 2. So response 1 and response 2. And they just happen to be binary responses. So this is what the actual data looks like. The key is that every individual in my data set just has one row to it. Everything that we know about that individual is in one row. That's called the wide format. What I can now do is transform this to the long format. So now what I want is to have a new variable called response that contains both response 1 and response 2 in it. And the corresponding rows are properly properly identify that if this is the response for subject 1, subject 2, or subject 3. So here we go. To transform it to the long format, I use Reshape. I specify where my data is. And then I specify, well, what's a variable that uniquely identifies every individual in my data set. And I say id var equal id.name, because that's where the names of the people were. I could have used id.number. I could have. Especially in settings where people might have the exact same name, the id.number would probably be unique rather than id.name. Then, well, what are my random variables? So I put those in my varying argument, varying response 1 and response 2. So these are my responses. And then what do I want to call then this new variable that's going to appear in my data set that has all the responses in it? I decided to just simply call this response. Direction equal long, meaning instead of the data set being wide, it's actually going to be quite long, as you will see. And if there was any variables that I don't want anymore, I could just simply drop them. Okay? So I put this into set 2, and this is what I get. So you can see, here's subject 1, And here's subject 1 again. At time 1, it had a response of 1. At time 2, it had a response of 0, just like what we had above. Now, this variable here called time is not one that we actually, you can say created through that reshape. Reshape did that for us because it needs some way of saying, okay, this was like the first observation for subject 1. This is the second observation for subject 1, and it needs some way to uniquely identify that. And since this is often done in a longitudinal data format where you're observing data over time, that's why it chose to call this variable time. If you look at the help of reshape, you could change that. But it just often makes sense to do that. Notice how for subject 1, the age variable, which we did not specify at all in our reshape, can't carry forward. And that the exact value was repeated for every subject in every row. For every well, I think you know what I mean. Okay? Notice how, of course, id.number did not come with us in this set too. Now, what's a little bit of annoying, let me do some erasing here. Of course, all my red marks sometimes are annoying. What's a little bit annoying is all this extra stuff that we get there. Those are the row names. And as we saw last time, we can actually remove those row names through saying row.names, give the data frame, and put in a null. And now they're gone. Any questions? So now that I have the data in this format, let's transform it back to the wide format, just to prove to you that indeed you get back to where you started. Okay, so again I use reshape. My data is now in set 2. My time variable, again this is the thing that's indicating this response 1 or response 2. Remember that variable name was called time. What uniquely identifies every subject or every individual in my data set? Well, that's id.name. Direction I want to go, I want to make it back to a wide format. My variable that I want to do this for is response. And I'll explain what SEP means in a second. And so I put this all in the set 3, and what do you know? Now I do have the wide format. Okay, so this SEP. By default, what R will do is put that time value next to the variable which was called response. And we'll actually put a period there. Response period 1, or let's say response dot 1. And we'll say response dot 2. That's the default. And when I put SEP for separator, equal quote, quote, that means don't put anything in there at all. So that's how I got back to having response 1 and response 2 exactly like what I had before. Any questions? Again, not necessarily the most interesting aspect to programming in R, but this can be extremely useful to change the format of your data like this. Okay. Now, let's also talk about another useful function called aggregate. You've actually seen this already in an assignment, so we'll review that a little bit, but we'll also look at some other uses with it. And basically what aggregate does, as you found out, it allows you to summarize variables by groups. Okay? So for example, let's say I have my serial data set. Once again, I transform my serial data set, sugar, fat, and sodium like usual. And then what I want to do is simply find the mean sugar content per shelf. I think we've seen something like this very similar with that NFL data. And so I say aggregate formula equal. What do I want to summarize? I want to summarize sugar. And then what do I want to summarize by? Shelf. And so this is very similar to a formula argument that you see with the LM function. response, given the covariate, and you separate them with a tilde. Where's my data? It's in serial. And how do I want to summarize them? How do I want to have some fun? Well, in other words, what's the function I want to use? Fun equal mean. And so that's how I get my mean sugar content per shelf. Now, some of you, I believe, in the assignment actually use a little bit of a different syntax there. You didn't use the formula argument. But I like the formula argument because it relates to modeling functions, not just LM, but many other functions that you'll see in your careers here. But also it's more general. Okay, well, let's say that you want to summarize more than one variable. So let's say I want to do sugar, sodium, and fat. And the syntax is exactly the same, except for now I need to put all my responses together. Now you might be thinking, well, how about sugar plus sodium plus fat? Because we've seen before with the LM function, if I have more than one explanatory variable, I just say x1 plus x2 plus x3. Why don't we do that with the stuff that's on the left side of the tilde? I don't know. This is the syntax that you have to use. So cbind stands for column bind. I'm putting columns of information together. You'll see cbind a little bit later in the matrix algebra section. And so that's all that this means. Let's put these columns together, and I'm going to now summarize each of those columns by shelf. And as you can see, here are the actual means. Really quick. Well, what happens if you have a scenario where not only do you want the mean, but you want to also get some other summary measures, such as maybe the standard deviation? Well, you could do that. The problem though is that you can only specify one function there. I can't say do the mean and the standard deviation. Instead, what I need to do is actually write my own function that I could put there that does all the summary that I need. So what I decided to do was create a function called mean.sd. My function, I'm going to pass in one thing. For the lack of a better name, I'm going to call it x. And this is simply going to be where my data is. And of course, remember the last line of the function is what's returned to the user when you use it. I'm going to combine together the mean and the standard deviation. Now, one thing that I didn't do here that's always good coding practice is actually try this function out on simply one, let's say, vector of data. So let's go ahead and do that for emphasis. Okay, so here's my function there. I'm running my data. Oh, don't give me that. Oh. It's just amazing how well this works in my office. Maybe we should just have classes in my office. And you can see that indeed it does work. Okay. Let's do it the old-fashioned way. I'll copy and paste. Let me make this a little bit bigger. Okay. So this is what I would typically do in one of these situations. I strongly recommend that you do this always. I'm going to try this function out on one of the variables. And indeed, it does work. I could verify that indeed the mean and standard deviation is that. So the big picture here for this side note is that whenever you write your own function, try it out in a simple case first to make sure it works before you try to do it in a more complicated setting, such as with the aggregate function here. So for example, aggregate, and I'm going to combine together sugar, sodium, and fat. Here's where my fun is, mean.sd, and when I copy and paste this, there's all my means and standard deviations. Notice sugar.1 is actually the mean. Sugar.2 is the standard deviation. Why is it the second one? Well, it's because that's what was returned second by that mean.sd function. That's why. So, very quick ways that you can do summaries like this. Are there any questions? Now, if you, let's say, had a grouping variable, we had shelf here as our grouping variable, but if you have, let's say, more than one grouping variable, what would you do? Well, similar to the LM function with the formula argument, you just simply say like x1 plus x2. You wouldn't do the c-bind stuff. Again, it's the syntax that's just required. And lastly for this section here, let's talk about how we can find subsets of a data frame. We basically have done this many times before, where the key is if you have some kind of data frame, let's call it set 1, that in the row argument, you put some kind of vector that has trues and falses in it. The trues would pull out those rows, the falses do not. And so, for example, with the serial data set, if I want just shelf 1, I put in some vector of information and that will produce the trues and falses for corresponding to shelf, and that's how I get shelf 1 information out. And in fact, if I wanted to, I could specify, well, I just maybe want columns 8 through 10. Alternatively, if I wanted to, I could specify the actual variable names within the data frame too. This is nothing new. Now, another way that sometimes you'll see people do this is to use what's called the subset function. I don't ever use it. The reason why I'm pointing this out is because I do see some people use it. Maybe the one advantage is that the syntax is a little prettier. It's a little bit easier to read. But majority of people will do something like this here. But again, I like to show you some stuff where if I see a number of others use it, I want to show it to you because you may run into this yourself. So, subset, my data is in serial, and how do I want to subset it? This is where I put shelf equal 1. And so you can see in this particular case how it will be confusing if I have just a single equal sign there for shelf equal 1. And so that's where that syntax of a double equal comes about and why it's needed. And then, well, what variables do I want to select out of the data frame? And I just put sugar, fat, and sodium in there. And indeed, I get exactly what we had before. Let's say, a common thing that I need to do when I'm using R is that maybe I'm looking for just one observation that fits some kind of criteria. Maybe it's the minimum sugar content of all the cereals, or something like that. And so what I might do is something like this. Suppose I want the minimum sodium value. So again, one way to do it is to create a vectors of trues and falses. So serial $ sodium equal the minimum of all the sodiums. It just so happens there are 2 cereals that have 0 sodium content. And so what's returned is actually 2 rows in my data frame. In terms of the subset function, you do exactly something very similar. Again, subset, my data is in serial. How do I want to subset? Sodium equal minimum sodium. Notice that I do not need to say like serial $ sodium because I already have a serial right there. And of course, I get the same results back. Okay? Now, there's another function that can do some of the same kind of things. It's called the which function. I see this even less than the subset function, but you do see it sometimes. You're welcome to take a look at it further on your own if you're interested. I do not have, unfortunately, any examples on my program. I never use it. Any questions? Okay. Now, to close out this section, I want to tell you about these 2 packages here. You are not responsible for these packages on the test. Just for time considerations, I decided to basically skip this. But I do want to mention them. Okay. So I think I've mentioned this individual before, Hadley Wickham. He's one of the most well-known people in statistics right now. He's written a number of books, and he's heavily involved in the development of R. He works for RStudio. One of his most popular package is probably the ggplot2 package that I briefly mentioned earlier. It allows you to do some graphics. And so Hadley has a number of packages out there that lots of people like to use. In particular, there's one called Plier, and with it sometimes it's helpful to use his Reshape 2 package. To be honest, I don't use these very often. I think maybe for one assignment, I did have you use something from the Plier package, and because it was the most convenient way to do some things. But basically, these packages do a lot of the same things that we just got done talking about with respect to Aggregate, with respect to Reshape, with respect to like the apply function that we've seen previously. They do a lot of the same things, and some people think that they do them better. Maybe, I don't know. You know, when I teach people how to do stuff in R, I always begin with, what can you do with the base implementation of R in terms of what functions come with it, what packages come with it by default. I start there, and then if there's something that is better in another package that you have to download, I will go ahead and do that. If there's something out there that a lot of people use, I will sometimes also talk about them in class. This is one of these examples here. You know, again, you know, in our particular class, you know, this is supposed to be a 2-credit-hour course. You know, there's a limited number of time. There's a limited time that we have available. I can't always keep on showing you how to do exactly the same thing multiple ways. You know, that's some of the compromises I think we've had to make, like you know, with respect to the SG procs in SAS and the G procs in SAS. So anyway, so I just want to briefly mention something about specifically Plier. So people call it Plier. Well, where does the name come from? Remember the apply function? It allows you to apply another function to a matrix, to a data frame, by rows or by columns. And so the Plier package gives you some tools that are very similar to the apply function and the various other apply-like functions that are out there. And so the PLY for Plier comes from that part right there of apply. The R comes from, this is R. And the way that and there's a number of functions in the Plier package that are set up the following way. Oops. This is a little typo right there. Excuse me. That R should not be there. So there's a number of different functions in the Plier package that are set up the following ways. You have a letter. PLY then is the rest of the function name. The first letter that goes there says, what form is your data in? So if you have a data frame, you would put a D there. The second letter says, what form do you want the result from applying this function to go out to? If you want a data frame as a result, you put a D there. So in this particular case, I show you how to use the DDPLY function. And all this is doing, this is with the serial data. You take the serial data. How do you want to summarize it by? Shelf. I want to apply it. I want to subset it by shelf. And I want to work with the sugar, fat, and sodium variables. And also do some find the minimums. Okay. Now there's a DLP, a DLP-LY function too, which says, okay, you got a data frame. I want to apply some stuff to it. I want the result to come out in the more general format of a list. There's a number of these functions just like that, all with the same last three letters, just different on the first two letters. Okay? You're welcome to take a look at this more on your own, but again, you are not responsible for it. I do have a number of examples. Like I said, in case I didn't say it, I rarely use stuff from this package. And lastly, I want to talk about SQL, or SQL. This is a non-statisticians, I should say, like to use the SQL language to manage data. Most people call it SQL, but you can call it SQL as well. SQL stands for Structured Query Language. It allows you to, let's say, for example, extract things from a data set, do some stuff, various manipulations with the data set, similar to like what we've been doing in this section. But this is primarily has been something that non-statisticians have used in the past. But since a lot of non-statisticians have migrated to using R, you will see some packages in R that are set up, you trying to use that same language format that you would see in SQL. There are some packages there that I give you. If you want to take a look at it on your own, you can. Nothing on the test will be from this here. Are there any questions? Okay, let's move on. Let's talk about matrix algebra now. Excuse me. So this is just some of the basics of how to do matrix algebra with R. So let's consider this setting where I have two 2x3 matrices. I have a matrix A, I have a matrix B, and I like to do some stuff with them. Okay? First of all, how do I get the matrix into R? Well, we've actually already seen the matrix function a little bit before, but we're going to look at it in a little bit more detail now. So let's create this matrix A here. And again, I use the matrix function. And in the data argument, that's where I want to put the numerical values that fill up the matrix. So I just combine together in what R would refer to as a vector all my data values. So as you can see, it's just simply 1, 2, 3, 4, 5, 6. I specify how many rows do I want. So number row, number of columns, and col, 3. And then lastly, by row is equal to true. And I think we've discussed this before. This controls how things are put into the matrix. What ordering? Are they put in by row or are they put in by column? So by row, look what happens here. So the first three numbers here, 1, 2, 3, are put in the first row. So it just simply fills up rows first, the row 1 first, and then it goes to row 2. If instead, if I would have had by row equal false, which is actually the default, then my matrix would have looked like this with the same, otherwise everything else the same syntax. 1, 2, 3, 4, 5, 6. So it filled up the columns first. It's obviously very important that you understand how R fills up the matrix. I think it's easier to think in terms of putting stuff in by rows, so that's why I always put a by row equal true there. Also, let me get my actual program out here. Something I usually do, or I always do, I should say, when I actually type it out in my program itself, I will always line everything nicely up so that you can actually see the matrix there in comparison to what you see in my syntax here. knitr and licks automatically transform my code so that it was just all together in one line. So that's why you see that. But I strongly recommend, just to avoid mistakes, that you do something like this instead. Actually put the stuff into different rows. Okay. Now remember, every object in R has a class. This class is always very important because it controls how generic functions operate on objects. So, whenever I'm faced with a new function, what I typically do is, especially if I want to do something with the result, is I always look at, well, what's the class? So I look at the class, and guess what? It's called matrix. Okay? Nothing surprising there. To access parts of the matrix, you do what you would expect. If I want row 1, column 1, I just put that into the square brackets. If I want just, let's say, the first row, I just say 1 comma. If I want just the last column, if I just want, the first column, I say comma 1. That's it. So let's also get this matrix B in here as well. And let's do some basic math. So if I do A plus B, as you would guess, it's just simply going to add the corresponding elements of the matrices together. If I do A minus B, it does what you would expect. No big deal there. Okay. Now the next stuff might be a little bit confusing for new people to R. Okay. Let's say I just have a mathematical vector. So it has a column vector would have a certain number of rows, 1 column. Let's create a mathematical column vector in R. You could do what you expect. Matrix, data, let's say I just want a vector 1, 2, 3. Number of rows 3, number of columns 1. In the end, by row equal true doesn't really matter because I only have 1 column. And I put this all into Y, and there's my mathematical vector. Of course, a mathematical vector is a special case of a matrix. But let's do this instead. So what I've been calling in the past, when I doing something like this, where I combine together using the C function, I've been calling that a vector. That's a vector in R's terminology. It's not necessarily a mathematical vector. And that's where the confusion can come in for those who are new to R. So if I put this into X, look how R reacts. It just simply writes out the numbers. You don't see both a row and a column dimension, unlike what we did here. There's column 1. There's rows 1, 2, and 3. You don't see that. And look what happens when I say class. Class of X, it's called numeric. And so you might be thinking, well, wait a second, why isn't it called vector? Because you've been calling this a vector. Well, it is actually a vector, but classes don't necessarily have to have that same name as the function that was used to create it or whatever. And so there are a number of functions in R that are called is dot, and then whatever you want to call maybe a class or whatever you're working with. If I say is dot vector X, it says yes, it is a vector. Okay, yes?
Would it say true if you asked if Y was a vector?
No. Maybe it's good it's the end of the semester. So it says false. Or I could say is dot matrix true. Maybe it's actually kind of confusing, to some respect. I know I was always confused with this when I was first learning how to use time was S+. That a vector and a matrix are different things in terms of R. There's a mathematical way of thinking of vectors and matrices, and there's an R way of thinking of vectors and matrices. They are different. Very often, you can get away with not paying attention to those differences. I We'll show you that very shortly. But there will be times where, if you're not careful, where it comes out like, oh, why isn't this working? This should work. And a lot of times it's because the things that you're maybe, let's say, trying to multiply together or whatever you're trying to do are different classes. And that's why. And so it's always important to understand the class of an object. Okay. So let me make sure I'm doing this. So just to show you one other thing here. So number of rows. So if I use the function n row for y, and also n col for y, you get what you would expect, 3 and 1. If I do n row x, error. N col x, error. Oops. Well, it's because I haven't done the x part yet. That's why. Let's do it again. It says no, because it doesn't exist. So a vector has essentially just one dimension in the end. A matrix has 2 dimensions. You could do this. Length of x, 3. What do you think would happen if I did length of y?
No.
Wrong. 3 as well. You might be thinking, wait a second. Okay, maybe that makes sense, but what is it actually doing? Well, let me get this matrix A in there. It's just counting the number of all the elements in it. Okay? So, let's see. I'll do that one. Now let's try to answer that question on your own. How would you create a 4x4 matrix of 1s? There's obviously a number of different ways to do it. You could use the matrix function in some way. You'll actually see some other ways to do it as well. Let's talk about matrix multiplication. So I have 2 matrices. A is 2 by 3, and B is 3 by 2. So if I take A times B, of course I get a 2 by 2 back. Or if I take B times A, I get a 3 by 3. How do you do matrix multiplication in R? You don't just say simply A asterisk B. It takes a while to get used to it, because normally you would think, yeah, I'm just going to do that. No. You have to say A percent asterisk percent. That's how you do matrix multiplication in R. The asterisk is actually reserved for something else, as you will see shortly. So I create my A matrix. I can create my B matrix. When I do A percent asterisk percent, you get that 2 by 2 matrix back. When I do B percent asterisk percent A, I get the 3 by 3 matrix back. You can verify on your own that indeed that is the correct values. Well, what happens if you do A asterisk B? You get an error message. Here's why. Suppose we look at the case of A asterisk A. So notice if I do A asterisk A, it's a 2 by 3 and a 2 by 3. The key is they are exactly the same dimension. What R will do is element by element multiplication. So we'll take the first element of A and multiply it by this first element, the 1, 1 element of A, multiply it by the 1, 1 element of A. Again. So just a plain asterisk is element by element, or you could say element-wise multiplication. What happens if I take 3 asterisk A? Well, this does regular old scalar multiplication. 3 is a scalar value, and it's just going to take the 3 inside each of the elements of that matrix A and do the multiplication. Well, let's consider working with a mathematical vector. 1, 2, and 3. Now, if I wanted to, again, I could use the matrix function And R would interpret it as we normally think of as a mathematical vector. But instead right here, what I'm going to do is show you what happens if I treat it as a R vector instead and try to do so this matrix multiplication. It's important for you to understand the end result. So X gets, I'm going to combine together 1, 2, and 3. And this A, remember that this is a 2 by 3. Thank you. This A is 2 by 3. And, this X up here, in terms of a mathematical context, is 3 by 1. So the end result should be a 2 by 1 if I were to do regular old mathematics on it. Well, let's see what happens. A percent asterisk percent X, I get that 2 by 1 vector. This is what you would normally have for A times X. But I've been just talking about here that X has only one dimension. It doesn't have a row. It doesn't have a column dimension. So how did R know to do what we would like it to do? What R does in these situations, when you have a matrix times an R vector, it will promote that R vector to a row and column dimension so that the matrix multiplication works. That's how R behaves. So in the end, someone can get away with not knowing that indeed that, when I form a vector like this isn't really a mathematical vector. One can get away with not knowing that in this situation. And it still will work out. Well, what about, suppose I did X percent asterisk percent X. Okay, again, in this situation, these X's are not 3 by 1 vectors. And normally, if they were 3 by 1 vectors, this shouldn't work. So you take a 3 by 1 vector times a 3 by 1 vector. You need to transpose something so that the correct dimensions work out. But look what happens here. R actually finds X, the transpose of X times X. And so when R is faced in a situation such as this, where you have two vectors are multiplied, two R vectors that are multiplied by each other, what it does, it finds what's called an inner product, which just simply means you multiply the corresponding elements by each other and you sum them up. It's an inner product. While I've never had a real reason to do this, there is actually something called an outer product, which would do the equivalent of X times the transpose of X. So a 1 by 3 times a 3 by 1 times a 1 by 3, you get a 3 by 3 back. That's called an outer product. And you can see the result there. So again, it can be a little bit confusing to know how R behaves, but it can be very important at times. I've faced this a number of times in my R programming lifetime, where I need to know exactly what was going on. So that's why I wanted to take the time to do this. Of course, as I said before, you get away with not worrying about this by actually using the matrix function. Okay, let's talk about finding the inverse of a matrix. Surprisingly, at least it was a surprise to me when I first started learning S+, there is no function called inverse. There's no function called inv, or anything close. Instead, there's a function called solve. And solve finds an inverse of a function. I'm sorry, the inverse of a function. Inverse of a matrix. I'll explain why it's called solve shortly. First of all, let's just show how to do this. So I'm going to create a matrix. Notice it's going to be 2 by 2. And I'm going to find the inverse of it. All you do is say solve, and then the matrix. That's it. Just to verify that indeed that this is a matrix, I could take A multiplied by the A inverse, and you get something very, very close to the identity. It's close enough for me. So also with this solve function, you can use it for another purpose. You know, when you have a system of equations, you can often write it out such as this. A times x is equal to b. And you try to solve for x. Notice the word solve. And so if one wanted to, one could create the matrix A, one could create the matrix B. Often it's just a vector. And solve A comma B will return back to you x. So that's another use for solve. And this other use then leads us to why the solve function is used to find an inverse. Suppose that B is the identity matrix. Okay? If it is, then you can see how solve is used to actually get the inverse. Because you just have A inverse back as your x. That's why there's no inverse function directly in R. Some more matrix operations. Let's say you want to find the diagonal elements of a matrix. So here's my 2 by 2 matrix again. And if I want to find the diagonal elements, I use a function, as you might expect, called diag. If I want to create a diagonal matrix, well, I just use diag again. But now for its argument value, I just put in a vector of values that I want on the diagonal. That's it. If I want a determinant of the matrix, use the det function or det function. And if I want a transpose of the matrix, I use the t function. Nothing really surprising there. Well, what about eigenvalues? Can R find eigenvalues? Yes, it can. It's done pretty much as you would expect. So I'm going to skip it. Just be forewarned that I have seen some small differences between what 32-bit and 64-bit R can produce when it comes to the actual eigenvectors. If you remember from your mathematical linear algebra, matrix algebra days, you know that eigenvectors are not unique. And they simply, in 32-bit, one can be, let's say, the negative of what you get in 64-bit. That's all. And so please see this on your own. I have some nice cool plots to show you that indeed eigenvectors are perpendicular to one another. Some additional comments. So all the functions that I talked about here are in the base package of R. There is, as you might expect, many other matrix algebra functions that you can use. A nice summary of them is at that web address there. There are also other packages out there that do matrix algebra that are set up to be, let's say, more efficient in certain settings. Like, let's say, if you have a sparse matrix, or if you have a very large matrix. And so the matrix package, the big algebra package are all useful for that purpose. And in fact, there is a nice task view that summarizes various things with matrix algebra that you can do. At times, you might have some data in a data frame. And if you want to do matrix algebra with the stuff that's in the data frame, often you need to transform that data to a matrix class. How can you do that? Well, there are a number of functions in R that start with the word as, and then they have a dot, and then the class name. So if I put a data frame inside the function as.matrix, that tells R to try to convert that data frame to a matrix. And then I can do matrix algebra with it. There are times when one needs to add a row or column of numbers to a matrix. So for example, let's say if I have two appropriately sized matrices A and B, I might want to basically vertically concatenate them. The way to do that is to use that cbind function that we've seen earlier. If I have two appropriately sized matrices, called A and B, and I want to put A up here and B down there, I can use a function called rbind to do that. Row bind. Also, very often you're left with a situation in simple linear regression where you're interested in this model here. And you can put all the y's and x's into matrices and stuff, and a vector of your estimated parameters. Just beta hat 0 and beta hat 1. You can find this by using what's often referred to as a design matrix. X is your design matrix, and you have x prime x inverse, x prime y. Now, how do you get that X matrix? That X matrix has a leading column of 1s. And so let's say, you have some data frame where you have a variable called X in it. So set $1 $X. So it has just all your X's in it. Maybe it has 10, 20 values. And you need to create a matrix, this matrix X, that has that leading column of 1s. What you can do is use cbind, 1 comma, then that X. So let's say that there are 20, maybe this is a high school and college GPA data set. There are actually 20 different high school GPAs, and there are 20 different values of X. Obviously, with that 1 there, there's just one value of 1. And so what R does, it will do what's called recycling. I mentioned recycling briefly before. It will recycle 1. In other words, it will repeat 1 as many times as it takes to match the length of what you have for X. So that in the end, you would have a 20 by 2 matrix. It's called recycling. And lastly, in this section, there is an argument in matrix called dim names, which stands for dimension names. Do you want to give your rows certain names? Do you want to give your columns certain names? The dim names allows you to do that. Sometimes that can be useful for descriptive purposes. Please take a look at the help for matrix to learn more about that. Are there any questions? Okay. Then that is all for today. We will wrap everything up on Thursday.